Okay, so before I start, how many of you have used this X-ray diffraction technique before? Okay, and how many of you understand how it works? Okay, so quite a few of you have used it, so that's good to know, right? So the first question, what are X-rays? So you use the technique, so you should be able to tell me what are X-rays. Huh? X-rays are a electromagnetic wave, right? So X-rays are a electromagnetic radiation, and typically they have a wavelength between 0.01 to 10 nanometers, right? And how do we generate X-rays? What you do is you shoot electrons onto materials, and that will lead to the generation of X-rays. So you can see here you have the X-rays at this part of the spectrum, and here you will see the visible part of the spectrum here, right? So generally, what we typically do to generate X-rays is that you have a tungsten filament. We heat the filament up. When you're heating this filament up, that is going to generate some electrons. And what we do is we take these electrons and you hit it to a certain anode. Now, this anode can be copper, it can be molybdenum, it can be iron, it can be cobalt, etc. And when you hit it with electrons at a certain accelerating voltage, that is going to that will lead to the generation of X-rays. Right? So, what is the most commonly used anode in laboratory?
Rhodium.
Copper. Why are we using copper as the most commonly used anode? Yes, the wavelength of the X-rays which you are using will depend upon the source, but why copper? Why copper? Why? Because practically you don't see all the materials being used for as a target. So why copper? Copper is the most commonly used anode for the laboratory diffractometers. There are some special cases where you can use molybdenum, cobalt, etc. But why is our choices of these material quite limited? It's not because of the availability, but one of the most reason is the fact that this process of hitting these anodes with electron is a highly inefficient process, and it leads to the generation of a lot of heat. So you should have a material which is conducting, and it should also be able to withstand very high temperatures, right? So that is what is practically limiting your options to the anode choices, and copper is the most cheapest source. Copper is what is easily available. So most of the laboratory equipments are going to be fitted with a copper anode, unless you are specifically going to look for something. For example, if you want to work with samples containing a lot of iron, then copper might not be the best choice, right? Because copper and iron has a certain interaction. It will lead to what is known as fluorescence, and that is going to create issues in your diffractogram, right? But for most of the applications for cement science, etc., copper, we can do well with copper itself, right? So typically when you hit the electrons to a target, it generates X-rays. Most of it's a very inefficient process. 99% of the energy is getting dissipated as heat. So that is why if you use laboratory diffractometers, there is always a chiller or a water cooling cycle. So that is to cool down the anode, right? And what is coming out of the X-ray tube is kind of a continuous spectrum with some discrete peaks, right? So the result when you hit electrons to a anode is going to be a continuous spectrum with X-rays known as white radiation. And what we see is the spectrum is a combination of a characteristic peak, which will depend on the type of anode which you are using, and a lot of background radiation, which is known as Bremsstrahlung or braking radiation. So this background is something which is called as braking radiation, and this is caused when an electron which is getting slowed down. Okay, you have an electron that is coming very close to another, the nucleus. It is slowing down, and that slowing down, the excess energy is getting released as the background radiation or the Bremsstrahlung. Okay, now this is something which we do not want. This is not going to be useful for us in our laboratory analysis, right? What we are interested is in the characteristic radiation. So this is something which you would have all studied in our 12th standard chemistry. When the electrons hit an inner shell, that gets ejected out, and electron from a L shell or a higher shell, it is going to come down to occupy its space, and that difference in energy is getting released as X-rays. Right? So, characteristic X-rays are emitted when an outer shell electron fills the vacancy in an inner shell of an atom, releasing X-rays. Right? And this is going to be very specific to the anode. For example, copper, they have a characteristic X-ray at 1.54 Armstrong. Right? Whereas if you are using molybdenum, the characteristic X-ray is going to be somewhere between less than 1 Armstrong. Right? So we are interested only in the monochromatic X-rays or analysis. So what we need to do is we need to filter out the unwanted, this background radiation, and you also need to remove the K beta radiation. So K beta radiation comes in when an electron from an M shell is coming down to the K shell. K alpha radiation comes in when an electron from the L shell is coming down to the K shell. Okay, we don't want this background radiation which is caused by the which is the Bremsstrahlung. We also don't want the K beta radiation. So what we need to do is we need to filter out these radiations so that the X-rays which we are using for analysis is a monochromatic X-ray with a fixed wavelength of 1.54 Armstrong. So what we can do is you can pass this radiation through a nickel filter. So if you look at your X-ray diffractometers, you will be seeing a nickel filter if you are using a copper anode. Okay, if you are using a cobalt anode, you will be using an iron filter. So the filter choice also depends upon the anode which you are using for X-ray diffraction. Right? So once you are passing it through a nickel filter or a monochromator, you can see that the entire background radiation has been removed. Your K beta radiation has been filtered. Right? Of course, if you want to get best filtration, you increase the thickness of the nickel filter. But the problem is, the more you are passing, the intensity of your K alpha radiation also reduces. Right? So then it becomes a compromise between the choice of your filter thickness and the intensity of the K alpha radiation which you need. Right? So what is diffraction then? Diffraction is the bending of waves around the corners of an obstacle or a slit. There can be two phenomena. One is constructive interference. So constructive interference, when these two electromagnetic waves are in phase, it gets added up. Okay, when two waves are out of phase, destructive interference occurs. So the amplitude get cancelled out. And this is again something which you all studied in your basic chemistry in your 12th standard. Right? So an easy way to visualize what happens is the classic Young's double slit experiment. So in this case, you have the light waves which are undergoing constructive and destructive interference to form this slit like the pattern of waxing and waning patterns. Right? So in the case of Young's double slit experiment, the interference is for the light waves, whereas in the X-ray diffraction, the interference, constructive interference, is going to be for the X-rays. Right? So that is an easy way to kind of visualize what is exactly happening. And what is happening is X-rays are having a wavelength of the order of few Armstrong, and this is very good for us. Why? Because the interplanar spacing or the atoms or the materials which we want to probe also have they also have this interplanar spacing which is very close to the wavelength of these X-rays. So this is the typical the wavelength of the X-rays which are generated is also the typical interatomic distance in crystalline solids. So that is why X-rays are a very good choice for understanding the science or understanding the nature or the structure of the materials which we are probing. Right? So the X-rays are being controlled, or the fundamental principles behind the X-ray diffraction is the Bragg's law, where you have your X-rays which are coming and those are getting diffracted from the crystal plane. So constructive interference for the X-rays will occur when the Bragg's law is getting satisfied. So that is n lambda is equal to 2d sine theta, where n is an order of reflection. Right, the first order reflection, second order reflection, etc. So lambda is going to be the characteristic wavelength of the X-ray which you are using. For copper, it's going to be 1.54 Armstrong. D is the interplanar spacing, and sine theta is the angle with which your X-ray is diverging from. Okay. So typically, lab scale instrument use a one-dimensional linear detector. So this is how an actual X-ray diffraction pattern will look like. You can see these circles, right? But in reality, most of our lab scale instrument only has a one-dimensional line detector. So the data is typically viewed as a plot of your angle versus intensity. You can see the circles here, the 2D diffraction circles here, and that is plotted as a function of your angle and the intensity. So the higher the intensity of these diffraction circles, higher is going to be your intensity on your diffractogram, right? There are latest equipments from Bruker which can actually measure the two-dimensional pattern by itself, but it's going to be a very expensive solution. For our work, this is sufficient, right? It is also important, there are two X-ray based techniques. So first is X-ray fluorescence. So what XRF does is it only gives you the elemental composition of your material, right? For example, your Portland cement, it will tell me that it contains 64.4% calcium oxide, 20% SiO2, etc. But it is not going to tell me how much of this calcium oxide and silicon oxide, SiO2, is present in the form of A light or in the form of B light, right? That is what we are interested in for identifying or calculating our hydration reactions and all those things, right? So your XRF gives us the elemental composition, and typically this is how the output is going to look like, a mix of calcium oxide, SiO2, L2O3, etc. Whereas your XRD gives you the phase composition, right? So this is something which is very important to understand and distinguish. So it is for XRD to work, you should have a crystalline material. So what is a crystalline solid? So crystalline solid is a material which has a regular repeating pattern with long range order, whereas an amorphous solid has no long range order, right? So crystalline solids are going to produce sharp diffraction peaks, whereas your amorphous solids are going to produce a hump or a background. It forms as a part of the background in your diffraction pattern. So there are 7 major crystal systems and the interplanar distance d, which is required to calculate the diffraction pattern. It is going to depend on the type of crystal system. You have your cubic, tetragonal, hexagonal, trigonal, orthorhombic, monoclinic and triclinic. All the phases present in the cement are going to be in one or other of these crystal structures. For example, C3S is most likely going to be present in a monoclinic form or a triclinic form, right? Your C3A can be orthorhombic or cubic, right? So for the Bragg's law to be satisfied, you need to calculate the D spacing, and this D spacing will depend upon the type of crystal structure present in your in which your material is present. For example, for a cubic structure, your D is very easy to calculate. D is going to be A, that is the lattice parameter, or that is the size of this cubic structure, the cube, divided by H, K, and L. H, K, and L are the Miller indices. Okay, so these are the Miller indices. For example, you have 0, 0, 1, HKL. So we are talking about this plane. If you have 1, 0, 0, we are talking about this plane. If you have 0, 1, 0, we are talking about this plane, and so on and so forth. So from this, we will be able to calculate the spacing, and we will be able to calculate the diffraction pattern for a cubic material. Of course, the calculation of D becomes more and more complicated as you are moving through the crystal system. For example, your monoclinic and your triclinic will be having more complex formulas to calculate the D spacing, whereas for your cubic structure, it is quite reasonably straightforward to calculate the D value, right? For example, this is the XRD pattern of NaCl using copper target. You can see that what are the diffraction patterns produced at different Miller indices, reflection from different HKL phase planes. Right? So the diffraction pattern which you are getting, it is going to be a combination or a sum of the diffraction pattern of the individual phases. For example, we know quartz, cristobalite and glass all are SiO2 in different forms or in different crystal structure. Right? So if you have a mix of quartz, cristobalite and glass, if you're doing an XRD on the combined pattern, you will see it is going to be a combination of the individual patterns. Right? So there are 3 different features or 3 important features for a diffractogram. The first is the peak position, which is typically marked by the 2 theta value. So what peak position tells me is the space group and the unit cell. It is going to depend on the space group and the unit cell dimensions of the phase. And if you want to identify, if you are given an unknown material, your peak positions are sufficient to make a very good identification of what exactly that material is going to be. So the peak intensities kind of indicate the abundance of the phase present in the powder, and these peak intensities are what we'll be using when we are trying to quantify the different phases using Rietveld analysis. and you have this peak width. So peak width is going to be an indicator of the size of the different crystallites and the effect of stress and strain. For example, some crystals are strained, there's going to be some stresses. That all will affect the width of the peaks which you see in the diffractogram. And typically for us in cement chemistry, cement applications, the size strain analysis is going to be very minimal. We are mostly worried about the peak positions and the peak intensities in the diffractograms, right? So how to prepare a good sample for the XRD? So generally experiments are going to be carried out on powder samples. If you want to work on hydrated samples, you could also cut some slices and you can do directly the XRD analysis on those as well. What is important to stress here is the fact that sample preparation is going to be very critical. That is, if your sample preparation is poor, that is going to lead to a very low quality data. You can do some kind of corrections during the data analysis, but it is always better to ensure that your sample preparation is good to collect the good quality data. So typically, if you want to prepare a sample, what you do is, this is known as a friend loading technique. You put the powder, you gently flatten it. You are not supposed to, it's not recommended to apply too much pressure when you're flattening the powder, so as to prevent or minimize the effect of this error known as preferred orientation. So this is how you prepare the samples. And the particle size. So this is another question which we frequently get, that does the particle size of the powder have an impact? Yes, the particle size does have an impact. So ideally the particle size should be less than 10 to 15 micron. That should be our target particle size. You could try to reduce the particle size by milling using a mortar, pestle, ball mill, disc mill, etc. But it's very important in the case of hydrated cement samples. If you are trying to understand the pattern of the hydration products, it's better to use a mortar, pestle, because if you're using ball mill or disc mill, the grinding might be too intensive and you might destroy the structure of the hydration products. So for hydration products, it's always recommended to use only mortar, pestle to prepare the powder. And you can see that as the powder is getting more and more, the particle size is reducing, the distinct independent peaks in the diffractogram is disappearing, and you can see mostly an amorphous hump here when the average particle size is reduced to 10 nanometers. So it's very important to ensure that your particle size is within the range of 10 to 15 microns if you want to get a very good diffraction pattern, right? And why should we grind the particles? Because we need to have sufficient statistics, sufficient particles to get a good measurement. So for example, if you have a well-ground sample, we have enough crystallites to get accurate intensities for the from the powder. Whereas let's say if your sample is underground, it is quite coarse. We don't have all the plane sects are not going to be detected. There is not enough crystallites in the powder to get accurate intensity ratios. So in this is the other reason why you should always ensure that your particle size is going to be ideally between 10 to 15 microns, right? So if the particle size is, if the sample is not ground correctly, you can see that you are having large crystallites. So single crystals are going to produce these spotty diffracted rays, whereas fine powders or crystals are going to generate very smooth diffraction rings. So we want this smooth diffraction rings. We don't want any graininess. For example, you can see that if you have a single crystal, again, you see these discrete points. Whereas if you have some powder, texture powder, there is some preferred orientation. You can see for the same diffraction circle, there are points of higher intensities and then points which is here. And then you have these points of very low intensities, right? Certain planes are being represented more. And if you have this powder pattern, a proper order pattern, you see a diffraction ring, and as the powder becomes more and more amorphous, the distinct ring is gone and it's just a amorphous sum. So this is how the particle size is going to affect the quality of your diffraction pattern, right? So the preferred orientation is something which is very common, and unfortunately some of the phases which we encounter in cement is known to have preferred orientation. For example, you have gypsum, which is commonly used. You have calcite, ettringite, etc. These are known to have preferred orientation. For example, this is a sample from the same cement batch, which has been prepared with and without preferred orientation. For example, you see here, you have a gypsum peak, which is very strong, and then you have a diffractogram with the gypsum peak very minimal. So why this is happening? The quantity of the gypsum is same, but because of incorrect sample preparation, the gypsum crystals are orienting along a particular direction, and that is going to create problems in your diffraction patterns. So the PO is a problem. It can be corrected mathematically when you're doing your retweet analysis to a certain extent, but results are going to be always biased. So it is always better to prepare your samples with random orientation. How to prepare random samples with random orientation? Just gently press the powder into the sample holder. That will ensure that you are able to minimize the preferred orientation. If you are doing a front loading, there are of course other sample preparation techniques such as back loading, etc., that can also be used to minimize the preferred orientation. So just to show you an example of preferred orientation in monosulfate. So this is the monosulfate pattern collected. You can see these large the peaks with very large intensities. I don't know if it's very visible. There are some small peaks here as well, right? So this is due to the extreme preferred orientation of the monosulfate crystal. So this is a zoomed in image. You can see there are more information here, but that is being lost because of the preferred orientation. So this is a typical what we know as a reflection theta geometry by reflection. You could also do a transmission geometry where you let the X-ray pass through the cylinder filled with sample, and you can see that this is how the original pattern should look like. So preferred orientation is a big problem, and it has to be minimized as much as possible. And coming to phase identification, like I have discussed before, you only need the peak positions. We don't need any other information. Some background information of the materials do help. For example, if I know that, okay, the material is some sort of clay, or if I know that the material is some sort of limestone, that helps me minimize, or that helps me make a short list of candidates to search, right? Typically, what we do is we compare the peak positions which we observe in the diffractogram with a standard database, and the standard database will be containing diffraction pattern of all these phases. And there are these commercial databases such as ICDD or ICSD, or you could also use the free database, the crystallographic open database. You can freely access it, and you can combine it with the free software such as Qualx2, that is open source, or you can use software such as Profix to do the phase analysis, right? So these reference patterns are typically represented by sticks, and the position and the intensity of the reference sticks should match the data. For example, we have these different patterns here, right? So this is the reference sticks from the ICDD, ICSD, COD databases. And the position, you can see, for example, you have hematite here. The position of the sticks and the relative intensities are matching very well. So both of this is important. The position and the intensity should match. A little bit of mismatch is okay. Why? Because when you're doing the experiment or when you're collecting the data, there could be some sample preparation errors. So in that case, a little bit of mismatch, a little bit of shift, that is still fine, but it should not be completely out like this. For example, this is a pattern. You see these two peaks are matching very well. The position and the intensity are matching very well. However, you see there is another peak which is here, which the database says it should be there, but in the actual diffractogram, that peak is absent. So that means the candidate or the phase which you have selected is not the good candidate, or this is not a good fit, or this is not a good identification, right? Also important, if you have some very minor phases, trace amount present, these peaks can merge into the background if the quantity is very low in the mixture. For example, you have 1%, 2% of a material, and you have a complex phase like cement, which typically will contain around 8 to 9 different phases. Some of these peaks might merge into the background, or into the or the peaks itself could merge. So in that case also, your search match is going to be a bit difficult, right? So other important point is people tend to guess the intensity or the quantities of the material present in the diffractogram based on the intensities. So that is not a very good practice. Why? Because the intensity with which a material or a mineral diffracts the X-ray is going to depend upon its material properties. For example, you see that this is a mix of TiO2, rutile and corundum. You see that the rutile peaks are more intense, right? So it would be incorrect to guess that the system or the mixture of this powder contains more rutile. In reality, this is a 50-50 mix of rutile and corundum, right? So the peak intensities are not, or it's not a very good representation of the actual quantity of the material present in your powder. right? So the pattern contains equal amount of TiO2 and Al2O3. The TiO2 pattern is more intense because TiO2 is a more efficient diffractor of the X-rays, right? So a question is like, is XRD a good tool to distinguish between the following phases, right? For example, you have calcite, magnesite, and siderite. So calcium carbonate, magnesium carbonate, and iron carbonate. Okay, they have the space group which are same, R3C, right? So is XRD a good technique to distinguish this? If I have a mix of these three powders or these three minerals, is XRD a good tool? Right? XRD might not be. So these all are structurally very similar. These are polytypes, right? What happens is they generate very similar diffraction pattern, and what is going to change is the overall size or the unit cell dimensions of the material. So XRD cannot directly provide you any information regarding the calcium content, iron content, or the magnesium content, right? So this is how the pattern looks like. What we'll have to do is we'll have to combine XRD with some chemical analysis such as XRF, ICP, EDX, etc. to clearly identify what is the elements present in your powder, and using that information we'll be able to shortlist, or we'll be able to correctly identify the different minerals present in the diffraction pattern, right? Now there is another question. You have different polymorphs of calcium carbonate. You have calcite, which is calcium carbonate, vaterite, calcium carbonate, aragonite, calcium carbonate. So is XRD a very good technique to distinguish these? It is. Why? Because these are all forming in different space group. So that means the patterns are going to be very distinct. Now this is an area where XRD is going to be very advantageous, because if you're doing a chemical analysis, because since all these three are calcium carbonate, you will not be able to distinguish if it is calcite, vaterite, or aragonite, whereas XRD is a very good technique because each will be having distinct patterns, because each are coming in different, or each minerals are having in different space groups, right? So to summarize phase identification, XRD is only sensitive to structural difference. It cannot tell you what are the elements which are present in it. It can tell you if your structure is in a cubic structure, if it is in orthorhombic structure, if it is in a triclinic structure, that you will be able to make a guess, but you will not be able to figure out if it is, if how much iron is present, how much calcium is present. You will need to do some basic tests such as XRF, etc. to identify it. Okay, there is very little information which you can glean from XRD on the chemical differences, and you will definitely need more complementary techniques to do a complete phase identification, right? For comprehensive analysis, combine XRD with chemical analysis. Of course, another thing what happens is people run it or use XRD like a black box. They do a search match pattern, and then they, whatever seems to fit or whatever gives a higher score, they blindly add it. It might be right, but it might be also wrong. So you will have to do a little bit of background. You should have some background information regarding the sample before you select a phase and say that, okay, your sample presents this material. For example, I remember a case where someone was doing an analysis and told me they found some very rare earth element in the sample, and I was like, oh wow, we are going to be rich. But then unfortunately what we realized that it was just a misidentified search match, right? So it's very important to clearly identify and not use XRD as a black box when you're doing the quantification. When you're doing the phase identification, right? Now phase quantification, now this is a place where XRD is getting a lot of value addition. For example, in most of the cement plants now you have an XRD, and they are able to automate the phase quantification. But again, Professor Shashank was mentioning, it's like throwing darts on the board, right? It can be an important tool for quantifying the various samples, but we need to clearly understand what are the limitations of the technique. We should not try to extract more information than what is possible. And we should be very careful not to overfit the data models, right? There are different quantification approaches which are available, something known as reference intensity ratio method, where you combine the intensity of the peaks generated by a very standard material, and then you compare it with the intensity of the peaks which you are collecting, and then you are able to make an approximation of what is the quantities present. You also have the whole pattern refinement, of which re12 refinement is going to be a big tool, And that is what is most commonly being used for phase quantification. Right? An important point to highlight is the fact that again XRD can only see crystalline material. If you have an amorphous material, for example, this is a mix of crystalline material, quartz, mullite, and this is a fly ash, you can see an amorphous hump forming here. Now that is because of the amorphous content present in your fly ash, and and this XRD cannot, or the amorphous phases or the phases with no long range order will not be able to produce any distinct patterns in your XRD approach. So this is a XRD pattern of your of a slag. You can see this hump. Now this is representing the amorphous content, and you could also see this background. So this is a background from the instrument. Right? So this is how a pure amorphous material, the pattern of a XRD pattern of a pure amorphous material is going to look like. So how do we do the Rietveld refinement? So basic principle of the Rietveld refinement is that every data point in the diffractogram should be fitted using a refinement model. So the parameters of the model, which could be the crystal structure, the sample, the instrument, and the background parameters, they are going to be simultaneously refined using the principles of least square minimization. So to put it in very simple terms, what we do is we minimize the difference between the calculated pattern and the experimental pattern. And once you minimize it, that is the principle of the Rietveld refinement. So before you start the analysis, what you need to ensure is that Rietveld refinement cannot be used for phase identification. Right? What you need to do is you need to very clearly identify what are all the minerals present in your sample. If you have an unknown phase, you'll not be able to do a Rietveld refinement, right? And Rietveld refinement is going to give you relative quantities instead of absolute quantities. For example, if I have a mixture of quartz and calcite, and I am just adding calcite to the structure and refining it, my Rietveld software will tell me my sample contains 100% of calcite. So if you don't put all the correct structure files, if you don't do a correct structure phase identification, your Rietveld refinement is going to give very erroneous result. Like I said, you need to have very good, excellent data quality, sample prepared with minimal preferred orientation, etc., with correct particle size to get good quality data. And you need to have excellent starting structure files. So typically, these good quality structure files will be available from the ICDD or the ICST or the COD databases. Right? So how do we calculate the pattern? So this is the calculated pattern. You have a scale factor, then you have a structure factor of the material, then you have a peak profile. It's a bit of complicated maths, which I won't go into right now. Basically, your calculated pattern is coming from a combination of all these information, plus the background from the instrument. And what contributes to the pattern? Of course, your scale factors or the intensity. That we will use to do the quantitative phase analysis. Your structure factor of the material, which is coming from the crystal structure. You have the profile function and the unit cell space group. All of this is going to be used when you're doing the calculated pattern. And when you're doing the Rietveld refinement, typically you will see that in this case, you have a calculated pattern and a measured pattern. You see the difference curve. You see that your peak positions are completely out of order. Our objective is to minimize this difference curve to the minimum as much as possible. You have your peak positions here, you have your absolute intensities, relative intensities, and peak width. Everything is mismatched, right? So this is not a very good refinement. How can we improve it? First, what we do is the wrong peak position. This is most likely due to the fact that your unit cell dimensions in your structure file is wrong. There is some sample displacement, there is some zero shift. That is, your sample is slightly higher than in the equipment. So typically, this is how, if you see this kind of a pattern in your Rietveld refinement, that means you have to refine either your unit cell dimensions, your sample height, or your zero shift, right? Once you refine your unit cell dimensions, you see that all the peak positions are matched now. So in the previous case, you see the peak positions were not matched. There was a mismatch, right? You see the peak position is mismatched. Once you refine your unit cell dimensions, your peak positions have been matched, but the relative and the absolute intensities are still wrong. So what you could do is you have to refine the scale factor. So when you refine the scale factor, your intensities are coming to be still close by. Now, once you do the refined scale factors, intensities have improved, but still there is a big difference in the difference curve. So what you do is, we'll have to start working out. First, we'll have to see if there is a preferred orientation effect. For that, we can do some corrections, graininess, atomic species, etc. For typically, we should not define all these parameters when you're doing a quantitative phase analysis. You should try to do preferred orientation and correct graininess and stop it at that. Right? So once you do the corrections, you will be able to minimize this difference curve as much as possible to a flat line. Right? Now, the other question is, how do we determine that we need to stop the refinement, or when is the refinement or when is the fitting of pattern good enough, right? So there are different parameters that the software will give you to analyze or judge what is a good fit. So typically we are interested in this RWP and the goodness of fit factor for cement and cementitious material. If your RWP is, once you do the refinement, should be less than 10 and a goodness of fit value less than 2, that means your fit is okay. Of course, the best way is to visually observe the difference curve between the observed pattern and the calculated pattern and ensure that it is minimal, right? And to get the best possible fit, you have to ensure that you are refining using a least number of parameters to get the best possible fit, right? So another important factor is we know that the instrument and the is going to contribute to a background function. So typically, if you keep on adding the background parameters, your fit will tend to improve. Right? That will lead to this excellent RWP goodness of fit values, but that is not going to give you any meaningful results. So ideally, we should use the minimum number of background parameters that is required and no more than that. So typically, depending upon the function you're using, anything more than 4 to 5 background parameters might be overfitting it. Right? The other problem which we face when you're coming into cementitious system is the fact that our hydrated cement is going to be a mix of amorphous phases such as CSH gel, your SCMs, etc., and some of a crystalline material like your C3S, C2S, etc. Right? So there are different material methods which are available, such as your internal standard method, your external standard method, and your partial or no known crystal structure method, also known as the Pong's method. So we'll discuss quickly what is internal standard method and external standard method is. So for the internal standard method, what happens is all your crystalline phases are going to be normalized to 100% weightage. So if the amorphous phase is not considered, all the other crystalline phases present in the system is going to be overestimated, right? So by adding a standard of known material, for example, you can add 20% rutile or 20% corundum to the sample. It is possible to recalculate the amorphous content. The standard will be overestimated, but we actually know what is the actual quantity we are adding. So we can back calculate to figure out what is the amorphous content. So the ratio of the actual versus calculated into 100 is going to give you the sum of all crystalline phases. For example, you have a sample with 60% phase A, 20% phase B, which are both crystalline, and you have your 20% amorphous content, right? And we don't have any standard, so this is the actual composition. If you're doing a Rietveld refinement with only adding crystal structures of phase A and phase B, we'll get that the software will tell me that your sample contains 75% phase A and 25% phase B, which is wrong. What we tend to do is we'll be adding 50% of a standard, right? So let's say I'm adding 50% of rutile to the sample. Now the actual composition is going to be 30% phase A, 10% phase B, 10% amorphous content, and 50% of the standard which we are adding. So when we do the Rietveld refinement, again, keep in mind XRD is invisible, or amorphous phases are invisible. So we'll get approximately 55.55% of your standard. And now we can use this 55.55% from the Rietveld analysis to back calculate the amorphous content. And this will be this is how you will be using internal standard technique. A known amount of material is mixed with the powder, and then we back calculate based on the Rietveld refinement. Okay, but there are different challenges with this method. First thing is you will have to ensure that your mix is going to be very homogeneous, right? You will have to take the two powders, you will have to grind it in isopropanol, you have to, so that the mix is homogeneous. The standard has to be a material of very high purity, because we are using that amount to calculate the amorphous content. So it should be 100% crystalline. So typically we use zincite, ZNO, corundum, Al2O3, or rutile as very common internal standards. Very important to ensure that the sample and the standard, should have the same mass absorption coefficient, why we will see now, and the sample and the standard should also have very similar grain size distribution. Right? Why this mass micro absorption or mass absorption is important? Because this is the most common source of error when you're doing your internal standard method. This occurs when the sample contains a mix of low and highly absorbing phases. Some phases can absorb X-rays more efficiently. Some phases will not absorb X-rays very efficiently. So if you have high absorbing material, the beam gets absorbed in the surface of the grain, and only a fraction of the grain is going to diffract the X-rays. Now what happens? The intensity which we measure in the detector is going to be less, and that will lead to a lower quantification value. If you have a material of low absorption, the beam penetrates the sample further, a greater likelihood of full volume of diffraction. That is, the entire data is coming out. The intensity of the peaks coming from a low absorbing material is going to be very high. So it is going to lead to higher intensities and higher quantification. Now this is going to be wrong. So this is why it is very important when you're choosing your internal standard, it should have similar mass absorption coefficient as that of your actual sample. And for cement, like I said, we'll be using corundum, zincite and rutile are very commonly used. Right? In order to overcome the pitfalls of this internal standard, there is this method known as external standard method. This is known as a K factor or the G factor method. So in this case, what we do is, we don't mix any samples. What we do is, we measure our sample. Afterwards, we measure a known material of very high crystallinity. And from there, we try to extract an instrument coefficient. And this instrument coefficient is used to plug in back to the analysis to get the amorphous content. Right? So amorphous content is derived as the same way as the internal standard. The difference being, you don't need to mix your internal standard with every sample. Let's say I have my 10 XRD samples. I run the 10 XRD samples. After my 10 samples are run, I run one external standard, rutile, zincite or corundum, under the same measurement condition as that of the we used to measure the samples. Right? Critical point is the fact that as your tube is aging, because let's say your tube is like 5 years, 6 years down the line, the quantity or the efficiency of your tube is going to reduce. So your K factor will also reduce continuously with time. So you cannot just do once, you have to do the external standard measurement every time you are running your samples. And the K factor or the G factor will be required to determine we'll have to redetermine it frequently to compensate for the tube aging, right? So of course, this has been prepared from a lot of references and acknowledgements due wherever they are. And so if you have any questions, I'm happy to.